Lesson 89 is on periodicity, and you should have looked over your rules and definitions for this lesson so you know that means the quality of being periodic, a pattern that repeats itself. That's what we mean when we talk about periodicity. And there's also a quote in your reading assignment from Alfred North Whitehead, and he said that one of the first steps necessary to make mathematics a fit instrument for the investigation of nature is that it should be able to express the essential periodicity of things. So when we think of periodic patterns, we think of cyclical things, and that is why we're talking about the unit circle in Part A. And so let's just think about some other things first here. I don't live in Alaska, but I love fishing for salmon there. Maybe you've been there. If you enjoy salmon fishing, you know someone who does, you probably know that every summer salmon return from the sea to spawn in freshwater streams. And the salmon life cycle, that's a fascinating story if you've read anything about that. Because of periodicity of the salmon life cycle, you can plan a fishing trip years in advance. And for example, if you wanted to go sockeye salmon fishing on the Kenai River in Alaska, you can plan a trip between the last week of July and the first week of August, and you'll be virtually guaranteed to catch some sockeye salmon and probably some king salmon as well. Now, like the definition says, periodicity is about repeating patterns. And because it's about patterns, like Alfred North Whitehead said, it's naturally about mathematics as well. One tool that helps us understand periodicity from a mathematical perspective is this thing called a unit circle. And by that we mean a circle with a radius of unity or a radius of 1. In math and science, that word unity is often associated with the numeral 1, but what does a unit circle have to do with a lesson that references 4 prior lessons on trigonometry? 19, 43, 59, and 78. Well, when you mix the unit circle, trigonometry, and coterminal angles together, the result is a tool to study repeating or periodic patterns. So think about a clock with an hour and a minute hand. Every hour the minute hand travels around the entire circle. But for example, if that was at 3:15 p.m., we'd have a little hand right there representing the 3, and I can't really draw them overlapping, but the big hand would be there representing 15 minutes. If that minute hand goes around one time, it's gone around 60 minutes, and then the hour hand is going to move some as well, right? It would be down here more, but we don't say that new time is 3:75 p.m. We say it's 4:15 p.m. We recognize the periodic pattern of time and identify it as 4:15. The minute hand is in the same place, but we realize that 1 hour has passed. The hour hand has moved. Now let's get back to this idea of unit circles. So to develop that, think about the 2 reference triangles you learned about in lesson 43. I have them shown there. And then let's create similar triangles, both with a hypotenuse of 1 or unity. So for the 45 degree triangle on the left, let's just redraw that here. We'd have the square root of 2x. We need to divide that by the square root of 2x. That means we divide everything by the square root of 2x, right? So this would be over the square root of 2 times x. This would be over the square root of 2 times x. So those x's would cancel, and we'd be left with 1 over the square root of 2 here and 1 over the square root of 2 here. So instead of an x square root of 2x triangle, we have a 1 over square root of 2, 1 over square root of 2, 1 right triangle. Think about the 30, 60, 90 right triangle. Let's just redraw one here, a similar triangle. And we can even put our little box on the corner there to remind us it's a right triangle. And for a hypotenuse of unity, or 1, we'd say 2x over 2x. That would give us 1, which means we need to divide this by 2x, this by 2x. Our x's cancel, and we'd be left with 1/2 here, and we'd be left with the square root of 3 over 2 on that longer side. So we have a half square root of 3 over 2, 1 right triangle there. Now here's where that unit circle idea starts to get interesting. Look at this unit triangle that I just put up. When the hypotenuse of a right triangle equals 1, the other two sides, they just equal sine theta for the opposite one and cosine of theta for the adjacent one to angle theta. I mean, try that on your calculator. You'll see that cosine of 45 is equal to the sine of 45. That's equal to 0.707. Now get your calculator out, and we can just do that right here, and we'll do 1 divided by the square root of 2, and that equals 0.707. 1 over the square root of 2 equals 0.707. So does cosine of 45, 0.707. So does sine, 45.707. You can try that with the 30, 60, 90 degree triangle as well. So here's your 30-degree angle there. That opposite side, sine of 30 does equal 1/2, and cosine 30 does equal the square root of 3 over 2. Now, look at this circle. It's centered at the origin of an xy axis. It has a radius of 1. So you see that here? And that segment right there, that's a radius of 1. So that's what the unit circle is about. Notice how you can draw in there a right triangle relative to that point. And its opposite side to angle theta would be sine theta. The adjacent is cosine theta. Now, let's keep going with this idea here, and let's think about the fact that depending on what quadrant it's in, any point on that circle there in the unit circle, that will have one of the 4 xy coordinates shown in the table below. So quadrant 1, it'll be cosine theta, sine theta. Quadrant 2, over here, say we had a point over here, whatever that theta angle is relative to the x-axis, then we'll get a minus cosine theta there and a positive sine theta there. Then the third quadrant would be minus cosine theta minus sine theta. Fourth quadrant, cosine theta minus sine theta. So what we're going to be doing here is we'll use the unit circle to help us locate and calculate sine and cosine values for coterminal angles that are relative to the 30, 60, 90 and the 45, 45, 90 triangle. So we're not going to be doing ones that are like 42 degrees or 31 degrees right now. So just considering that periodicity of the unit circle, that will help us make these problems easier. That's the plan anyways, is to use a unit circle to make this easier. Hopefully that's what's going to happen. So example 89.1, use a unit circle, not a calculator, to calculate sine theta and cosine theta when theta is equal to a of 30 degrees. So let's just start with a there, and let's go ahead and just draw a unit circle. So we'll make an xy axis here, and let's just, to the best that we can, we'll sketch in a unit circle here. It doesn't have to be anything fancy. So for A, we want to do 30 degrees on there and figure out what sine and cosine of 30 degrees are. So relative to that x-axis there, let's just estimate a location of 30 degrees. So something like that. And so a hypotenuse of 1. So this side then would be sine 30 degrees. This side is going to be cosine of 30 degrees. And look at your table that was given to you at the beginning of the reading assignment. Here we don't want to use a calculator on these. We want to get like an exact answer. So sine 30, that's going to be equal to 1/2. Cosine 30, that's going to be equal to the square root of 3 over 2. So hopefully that makes sense. That wasn't a very challenging problem there. Now B. This one we want to find sine and cosine of 225 degrees. So again, let's sketch out a unit circle here. Nothing fancy. So we have a circle. Now let's just go around to 225 degrees. So we think starting at the positive x-axis, 0 to 90, 90 to 180. So we still need to add 45 degrees on. So we're down here. So there it is, 45 degrees. That, go ahead and draw our triangle based off of that. So that hypotenuse is 1 there, and this side would be minus sine theta, and theta is what is in the triangle there. What is this right triangle? It's got an angle in there. That angle is a 45 degree angle inside that right triangle. So we're doing minus sine 45, and then this side over here is minus cosine 45 degrees. So both of those are in terms of 45. Minus sine 45 minus cosine 45. So look at your table at the beginning of the reading assignment. What does cosine of 45 equal? That equals 1 over the square root of 2, but this is minus cosine 45, so it's minus 1 over the square root of 2. And so cosine of 225, that equals sine of 225. They both equal minus 1 over the square root of 2. Now something to consider here is that normally the standard form, you don't have a radical sign, a square root sign in the denominator. So we can multiply above and below by the square root of 2. And we don't change anything because that's just multiplying by 1, right? It just changes the way it looks. So we end up with minus the square root of 2 over square root of 2 times square root of 2 is 2. So we got rid of that square root sign, and so that's another way to write that. Square root of 2 over 2. That would be the standard form to write that in. So on future problems involving 1 over the square root of 2, rewrite them in standard form like that. Square root of 2 over 2. Don't have the square root sign in the denominator. So we used the unit circle there to set up a right triangle. And that's an important thing to recognize here. We set this right triangle up. It's a 45, 45, 90 triangle, but it's, relative to the x-axis, we're thinking of 225 degrees. So we think of the triangle in terms of a 45, 45, 90. We think of the original question in terms of the original angle, the 225 degrees. Okay, let's move on to C. On 405, we want to find sine and cosine of 405 degrees. And here's where we're going to start getting into coterminal angles more. And so let's just draw our xy axis, make a unit circle here. And again, nothing really fancy, but just try to draw a circle on there. And let's think about 405 degrees. So we're starting at the positive x-axis, and we're going to go around 360. But we still have 405 minus 360. We still have 45 degrees to go. So let's go up to that. Then we'll go ahead and draw our hypotenuse in and our right triangle. So we see we have a 45, 45, 90 triangle. So 405, we can relate that to a 45 degree angle. That's our coterminal angle is 45 degrees. Just like on a clock, we wouldn't say it's 375, we'd say it's 415, right? So we're going to say here that cosine 405 is equal to sine of 405. Both of those are positive, right? So, and they're both equal to each other. Since it's a 45, 45, 90, they're both going to equal square root of 2 over 2. And so that would be our answer for both of those. And let's do one more. sine and cosine of 660 degrees. So one more time, we want to draw a unit circle. Notice that's always our first step on these, drawing that unit circle however closely to a circle that you can. And then we're going to think about our coterminal angle here. We're going to look at 660, and we know for sure we're going to go around 360 degrees, but we still have 660 minus 360 is 300 degrees to go. So we have to go all the way around again down to here. That would be about 300 degrees. Then we'll draw our hypotenuse in and make a right triangle. So if that's at 300 degrees, what's our right triangle? This angle right in here, let me change colors. That angle must be 60 degrees, right? So if the hypotenuse is 1, then this adjacent side, that must be 1/2. Cosine 60 is 1/2. Go look at your chart at the beginning of the lesson in the reading assignment. Sine of 160, and this is going to be minus, right? Because it's below the x-axis there. That's going to be minus square root of 3 over 2. So cosine 660, that equals 1/2. Sine of 660, that's equal to minus the square root of 3 over 2. So much of this and understanding the unit circle is just getting your bearings, thinking about where am I, what's my coterminal angle here. Find that, then set up your right triangle. It's either going to be a 30, 60, 90 or a 45, 45, 90 for now. Now you can get your calculator out and you can type in sine of 660 or cosine of 660 on your calculator if you want to. And let's just do that real quick. 660 cosine. What do you get? 0.4999, which is 0.5, basically half. What about sine of 660? It should be negative 0.866 or so. Let's see. It is negative 0.866. So you can check your work that way with the calculator, but remember on these problems, what are we doing? We're trying to get exact answers. So that's 1 over 2. This one's the square root of 3 over 2. There's no rounding involved, no decimals involved. Just the way the calculator calculated cosine of 660, it should have said 1/2, but just the method that's used inside the calculator, it came up with 0.4999 repeating, which was almost 0.5. And then negative 0.866, that's not the most accurate way to write that. The most accurate way to write it is minus the square root of 3 over 2. That doesn't have any decimals. We haven't rounded or anything. So that's what we want to do for problems like this that you see in your practice set. Well, let's move on to part B on vectors and sign changes. We won't be using the unit circle so much here, but we still need to keep in mind that idea of periodicity and coterminal angles. And maybe you remember back in lesson 59, you learned that you always measure positive theta relative to the positive x-axis, and you move counterclockwise until you're at the right location. But maybe you notice in example 89.1d that described a negative 60-degree angle. Right? We went around almost 2 full times and we ended up with that right triangle there that was 60 degrees below the x-axis. So in a way, this right here is negative 60 degrees. So notice how going down in a negative way, that's coterminal with going around in a positive clockwise direction 300 degrees. Notice how those are the same thing. So we can arrive at this side right here. We can arrive at that same location by going down 60 degrees, going clockwise 60 degrees, or counterclockwise 300. So just keep that in mind. And also, you may have problems where a vector's magnitude is given to you as a negative number, and you can make it positive simply by flipping it 180 degrees. So if you had something, for example, a vector that had a magnitude of -5, and let's say its angle was 45 degrees, so it's over here 45 degrees, and the magnitude is negative, you make it positive by flipping it around 180 degrees, locating it down there. So that's really where the vector would be, and that would give it a positive magnitude by flipping it around. So for vectors in Shorman mathematics, we'll consider them to be in standard form if both the magnitude and the direction are positive. So keep that in mind, with the direction written as the simplest coterminal angle possible. So if we had a 400 degree angle, that would not be the simplest coterminal angle. 400 minus 360 is 40. That would be the simplest way to write it. Let's just go ahead and do some practice problems now. So we've got several examples here, A, B, C, D, and E. Write those in standard form. Write those vectors that have been given in standard form. So that means positive magnitude, simplest coterminal angle. And we can solve all of these in 2 steps. First step is to locate the angle and record the smallest positive value that represents that. And then step 2 is, if the magnitude's negative, then reflect it 180 degrees and write the vector in standard form. If the magnitude's positive, then you don't have to do anything else to it. So let's do problem A. And first, on all of these, it's a great idea to just draw an XY axis and locate the angle. That's what we want to do first. So let's go ahead and do that. We're at 405 degrees is our angle, so that's in the counterclockwise direction. It's positive, so we go around 360 plus 45 degrees more. That would be positive 45 degrees. That's going to be the simplest way to write that. And then our magnitude is 6. So that's it. We have that coterminal angle in there that's equal to 45 degrees. And so we'd write this result as 6 angle 45 degrees. That's the simplified form there. B, 6 angle minus 405 degrees. So we've got the same magnitude, but this angle is going to go around in the clockwise direction, so be careful about that. Let's just draw our XY axis again to start with, and let's begin at the positive X axis as usual. Go around negative 360 degrees. Then we need to go around another negative 45, so we're right down here. Okay? So a negative 45 degree angle from there to there is negative 45. That's coterminal. Go around the other way. That's coterminal with this 315 degree angle. So remember, our standard form is to write the angle as positive, write the magnitude as positive. Our magnitude already is positive. It's 6. So the answer there is 6 angle 315 degrees. That's our standard form for that vector. C, negative 4 angle 60 degrees. So again, let's draw our XY axis first and locate the angle first. So that's just a 60 degree angle, so we just go up counterclockwise. We'll say that's 60 degrees right there. Then our magnitude is a minus 4. So to properly locate that magnitude, we need to flip this. We need to be down here, 180 degrees the other direction. So what would that be? That'd be 180 plus 60. That's 240 degrees is that angle relative to the x-axis, magnitude of 4. So our answer there is 4 angle 240. That's our standard form, 4 angle 240 degrees. Remember, the standard form is when we have our simplest angle, it's positive, the magnitude's positive. Both things are positive. Let's look at D now. This one we have a negative angle and a negative magnitude. So much of this is just getting your bearings at answering that question, where am I? So negative 60, that means we need to move clockwise. So we're going to move down 60 degrees. And we're just estimating here our location, but if you got a protractor out and measured that, it probably isn't exactly at 60 degrees, but that's okay. We're just trying to estimate the location. Down 60 degrees. So we'll say negative 60 there. And then our magnitude is negative 4. So we know we're going to want to flip this 180 degrees. So how can we figure out where that location is? Well, we know that the blue and the purple line are 180 degrees apart. So let's just try to think about this in the simplest way that we can. We went negative 60, then we went back 180. So minus 60 plus 180, that's equal to 120. So we're at 120 degrees here. That's this angle right in there. That's 120 degrees. This magnitude is positive 4. So our answer for D is 4 angle 120 degrees. That's the most simplified standard form that we can get for that one. So we have one more to do. E minus 5 minus 750 degrees. So got a coterminal angle to deal with there for sure. And let's just go ahead and locate that first. So we're going clockwise. We go around 360. We go around again. That's going to be 720. We still have 30 degrees to go, right? So we're going to be down here somewhere. Minus 30 degrees is what that looks like as a coterminal angle to the minus 750. And then this is a magnitude of negative 5. That means we need to flip it 180. So we're going back this direction 180. 180 minus 30, that's equal to 150. So starting there at the x-axis, from there on over, that's 150 degrees with a magnitude of positive 5. And so our answer there is 5 angle 150 degrees. So be careful on these. Get your bearings. Go with those 2 steps every single time. Step 1, we locate the angle. Step 2, we locate that magnitude and we flip it if we need to and adjust the angle accordingly. On D, step 1, we located that angle at minus 60. Step 2, we flipped the magnitude and located that, adjusted the angle. Okay, well that's all for lesson 89.